Welcome to this video for Hannah. This is on why transition metal complexes have color. There I have drawn an octahedral ligand field, and I've drawn in the X, Y, and Z axes. Why do I draw these? Well, because that's where the ligands approach from. So the ligand, I'm just going to use L, even though they're water in this case, aren't they? The ligands are coming on the axes, okay? All right. So let's have a look at a ligand, a typical ligand. Water is a ligand. A ligand. What's a ligand got? Well, first of all, it must have a lone pair because the lone pair is what bonds to the central metal ion. So the lone pair bonds to the central metal ion. So it's got to have a lone pair. Now let's pick, I don't know, I always pick water, so let's pick ammonia. This is ammonia. Okay, and ammonia has a lone pair, and the lone pair has its own electron cloud like that. Okay, all right. So when ligands come in, the lone pair on the ligand interfere with the d orbitals of the transition metal. So let's move this up a tiny bit. Okay, now I'm going to draw the five the 5d orbitals. So what are the d orbitals? Okay, always a lowercase d, by the way. All right, as I did in class, I'm going to draw 5 axes here. Not very good, but never mind, that will do. And I'm going to put my lobes between the axes. There, and there. So these all look the same, but they're in a different plane. The first one, this is the XY plane. This one is the YZ plane, and this is the XZ plane. So this one would be called the DXY, this one is called the DYZ, and this one is going to be called the DXZ. The other two orbitals are a bit strange. They're on, this one is on the axes, and these axes are the Y and the X. And the last one is on the Z, and it's got a donutty thing around the middle. So this one is the Z axis, okay? this one is either the X or the Y, it doesn't really matter. All right, so you've got your 5 d orbitals there. And the ligands, as I say, approach along the axes. So where's my ligand? My ligand, what color should I draw my ligand? Let's have a nice crisp color, that's purple. Okay, my ligand, there's the nitrogen, and it's coming on the x-axis, and there's the lobe. Here's the ligand again, coming along on the z-axis, and there's the lobe, and here it is. Oh, I've done it wrong, haven't I? Let's put one down here, coming along the y-axis, because I haven't got a y-axis to do on the last one. So let's put a ligand coming along the y-axis like this, and there you go. So the point is, for these three top ones, the ligands approach between the lobes of the d orbitals, but for the bottom two, the ligand actually goes on, or sorry, it overlaps with the d orbital. Like this, it approaches on the x, it will overlap with the x. If it approaches on the y, like this one, it overlaps with the y. And if it approaches on the z-axis, which they do in an octahedral field, it will overlap with the z. Okay, so these two are different. Here you have ligand, d orbital, overlap. Okay, and here you don't. No overlap. Or minimal overlap. They will overlap a little bit depending on the size of the lone pair cloud. Okay, so where you have overlap, you also have repulsion. And the repulsion between the ligand and the d orbital will push these two here, will push them to a higher energy level. Okay, so there you go. So that, and it's quite technical, isn't it? Quite a technical subject, this, but never mind. Okay, so hopefully you'll remember everything I've done. So let's have a look at the energetics of everything. Let's draw a nice axis here. And one along there. Now I'm going to do, because you've got to understand 1, 2, 3, 4, 5. This is when the ion is not in the water, when it's not being surrounded by water molecules. In other words, we call this one the isolated ion. Okay, this is an isolated ion. We often say fields because there's nothing going on. This is energy. All right, the next one I'm going to do is what we call an octahedral field. Now the ion is placed as an octahedral field, and as we've seen, the two at the bottom get promoted, and the 3 at the top, I've done it the wrong way around, haven't I? Up here, 3 at the top are not promoted, so there you go. That's in an octahedral field. So let's pick copper. Copper has 9 electrons. Cu 2 plus, I believe, is 3d 9. That's right, isn't it? So let's put my electrons in. 1, 2, 3, 4, 5. 6, 7, 8, 9, and it would look like that. Okay. Now, but when it's in, so all of these d orbitals, d electrons are the same energy. Okay, and we say they are degenerate. Degenerate. When we put it in an octahedral field, in other words, when it's in water, okay, the d orbitals split. So we call this d splitting. Okay, the d orbitals split like that, and now the electrons will get 1, 2, 3, 4, 5, 6, 7, 8, 9. They'll split into 2 like this. Okay, now the energy difference between these two here, all right, here, it's a tiny bit of energy, but it's delta E. It's going to be equal to HF, where H is Planck's constant and F is the frequency. All right, now this frequency is very important. If it's in the visible part of the spectrum, and they're not all, but if in the visible part, then the complex will absorb a color. Okay, I don't know what color it's going to absorb, but it will absorb a color, and therefore it will take a color from white light, and what we see is what's not absorbed. So we will see the complementary color. Okay, so for example, very basically, Richard of York gave battle in vain. Is if this frequency here corresponds to the red end, we don't see the red end because it's being absorbed. We see the blue end, and it will be blue. So that's why copper sulfate in water is blue, because it's absorbing at the red end. Okay, now different ligands change this energy gap. Okay, this energy gap can get bigger and smaller, and if it gets bigger, it will absorb more in the blue end, because the frequency will be higher, of absorption will be higher, and so we'll see a more reddy color. Okay, so one thing, or two things, I should say. Let's write these down so we don't forget them. What changes the energy gap? What changes, or affects, I should say, shouldn't I? What affects, or what changes the energy gap? Okay, number one thing is the ligands. Okay, the ligand gets really close, and that can widen up the gap. All right, there we are. There you go. So the ligand can, so this can widen it up or close it down. And the second one is the type of metal ion. Okay, that will change the energy gap. And the other thing is, even if the type of the metal ion is the same, the oxidation state of the metal ion. So, for example, Fe3 plus and Fe2 plus, they'll give different colors because they'll change this energy gap. Okay. Now, I don't know how long we've done. I didn't want to go on for too long, okay, because I don't want to bore people. But interestingly, and if you have a problem with this, give me a shout. If you have copper in a tetrahedral field, like it would be if these were chlorines, and this would be an ion, this would be 2 minus, I believe. Okay, we get the same idea as before, but because the orientation is different, now let's draw my degenerate set. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9. All right, because of the geometry is different. Geometry is now tetrahedral. If the geometry is tetrahedral, you get 3 at the top and 2 at the bottom. Okay, now the 3 at the top are the dxy, dyz, and the dzx, I think. The ones at the bottom are the dx squared minus y squared and the dz squared. Okay, so now if we have this situation, we have 1, 2, 3, 4, 5, 6, 7, 8, 9. We have delta E is here again. Delta E is HF, but we have an inversion of the d orbital energies. Okay, this one here, I didn't mention this, but this is the isolated ion field. Oh, how do you spell field? Field. This is the inversion, and we call this setup, when it's in a tetrahedral field, we say this is a tetrahedral ligand field. Oh, my pen is a bit slow today. Ligand field. Okay. All right. So basically, they will appear the color. This is going to be confusing. They absorb light in the visible, and they will appear as the color that they are not absorbing. All right, and we say they appear as the complement color. Hope this makes sense. If it doesn't, give us a shout, and I'll try and redo it. Bye bye.